Okay, so today we will discuss one of the most important rearrangement reaction, that is Favorskii rearrangement. Okay, so in this rearrangement reaction we have a alpha haloketones. Okay, so these are converted into carboxylic acid. Okay, so this is the common definition for Favorskii rearrangement. So in this rearrangement we have a base catalyzed. Okay, so it is base catalyzed rearrangement of alpha haloketones to carboxylic acid is called Favorskii rearrangement. Okay, so simply we can say that alpha haloketones are converted into carboxylic acid in the presence of base catalyst. Okay friends, so we have alpha haloketones means this is ketone group and this is alpha position. So in alpha position we have a halogen group. Okay, so this is called alpha haloketones and in the presence of base catalyst. Okay, so it converted into carboxylic acid, so this is called carboxylic acid. Okay, so these are the general reaction for Favorskii rearrangement. Okay friends, so X means here we can say chlorine or bromine, and your nucleophile act as OH, OR or NRR. Okay, so these are the nucleophiles. Okay, let's see the mechanism part for this Favorskii rearrangement reaction. Okay, so in this rearrangement reaction, first of all try to understand what is the mechanism. Okay, then after we will solve different types of questions related to Favorskii rearrangement. Okay friends, so let's discuss mechanism. Okay, so let's discuss mechanism. Okay, we have alpha haloketones. Okay, for example, this is an example of alpha haloketones. This R and this is R1. Okay, so you know that we have a base catalyst, so base means like that OR. Okay, for example, this is OR and this is base catalyst. Okay, so we know that base are generally attached to the H plus ion. Okay, so base are accept protons. Okay, so which proton will be removed from alpha haloketones? So this is alpha haloketones and here one proton will be removed because we have a base, so base are attached to the H plus ion. So we know that we have hydrogen here, so this is hydrogen group, so this OR group will attack this side, so this H plus will be removed. We know that when H plus will remove, we know that double bond C, this is R and this is R dash, this is X. Okay, so this is negative charge. Okay friends, we know that this is negative charge and this negative charge will resonance this side, this bond will shift towards. Okay, so R dash oxygen O negative. Okay, so this is the double bond, this is R and this is halogen group. So these are the resonance structure. Okay, so these are the resonance structure. Then after we know that this negative charge will shift towards this side, and this double bond shift towards this center of the halogen group. So then this halogen will be removed. So these are the process. Then we know that minus x minus. Okay, so in this case halogen will be removed. Then after we get 3-membered ring. So this is this negative charge, this double bond shift towards halogen center, then we get this type of structure. Okay, so this is R dash and this is R group. Okay friends, so this is the final structure, and we know that when double bond shift towards halogen center, this halogen will be removed, so 3-membered ring will be formed here. Okay, so in our solution we have OR minus. Okay, so in our solution we have a OR minus. So this OR minus will attack electrophilic center of this product. Okay, so then after this bond shift towards oxygen, so finally we know that oxygen negative charge and this will OR group. Okay, and this is R dash, this is R group. So then again this negative charge shift towards oxygen bond, then one bond will be removed, this bond or this bond will be removed. Okay, then this bond will be removed this side, then we get R dash double bond O, this is R dash and this is R group. Okay, and this is the negative charge. Okay, so when this bond shifts towards this side, then we get negative charge here. Then in our solution we have R dash OH. Okay, so in we have a base catalyst, so this after protonation this ROH group will gives H plus ion. So then after, okay, this H plus ion will attack to the nucleophilic center. Okay, so finally we get R, this is C double bond O, this is OR group. Okay friends, so this is the final product. So this can also be written as RCH2. Okay, so this is R and this is COOR. So this called as, this is ester group. Okay, ester group. So this is the final product. Okay, so this alpha haloketones is converted into carboxylic acid. So we know that ester is a example of carboxylic acid. Okay, so this is the final product. So okay friends, so this is the mechanism and this is the introduction about Favorskii rearrangement. Okay, let's discuss some related questions, then we will understanding better. Okay friends, so one more important point is noted that so in this mechanism we know that one cyclopropane ring will be formed. Okay, so in this case one cyclopropane ring will be formed. Then in this case one cyclopropane ring will be break. So this bond or this bond will be break. So the direction of ring opening of cyclopropane is depend upon the more stable carboanion. So okay friends, so this is the point, that the direction of ring opening of cyclopropane ring is more stable carboanion. So when bond will break, then we get carboanion. So that carbanion is more stable, then that product will be favorable. Okay, so that product will called as a more stable product. Okay, let's take some example to understanding. Okay, for example we will take pH, C double bond O, this is chlorine atom. Okay, so we know that MeO minus. Okay, so this is base catalyst. Okay, in the presence of acid. So we know that this base catalyst will remove H plus. Okay, so this will attack this side, one H plus will be removed. Then we get CH2. This is CH2. Okay, so this is methyl group. Okay, so CH2 negative charge, and this is phenyl group. This is chlorine atom. Okay, so this negative charge will attack halogen center of the product, then this chlorine will be removed. So then we get cyclopropane ring. Okay, so then we get cyclopropane ring, and this is phenyl group. Okay friends, this is the product. Okay, so in this case we know that we have a OMe group in our solution. This will attack this electrophilic center, then this bond shifts towards oxygen. So we know that this will be O negative and OMe. This is phenyl group. Okay, so in this case two cases will be occur. Okay, for example this double bond, or we can say this negative charge will shift towards carbon oxygen bond, then this bond will be break and this side also break. Okay, so these two bonds are break. So for example this bond, when this negative charge will attack this side, then this bond will be break, then we get what type of product? Phenyl negative charge okay, so this bond shift towards this side, so we get C double bond O Me. Okay, so when for example this bond will be break, then we get phenyl CH2 negative C double bond O Me. So these two type of product will be removed. But we know that this negative charge means this carbanion will more stable than this carbanion, because this is phenyl group. We know that negative charge will participate in resonance, so this negative charge will more stable. So this is carbanion, so more stable, because carbanion is more stable. So this product will be favorable. So this is major product, but this negative charge will less stable as compared to this one. So this is not favorable for product formation. Okay, so we know that this is a favorable structure. So then after we have MeOH, then we get final product phenyl, this CH2 and OMe CW. So this is the final product, major product. Okay, this is major product. So one point is not the direction of ring opening of cyclopropane is depend or determined by the more stable carbanion. Okay, formed in the reaction. Okay friends, so when cyclopropane ring will be formed in our mechanism, so the cyclopropane ring will be break when the more stable carbanion will be formed. So that side will be favorable product will be coming. So so these are the some concept related Favorskii rearrangement. Okay, so let's discuss some important questions. Okay friends, so we will take some example related Favorskii rearrangement. Okay, so this is okay friends, so this is a alpha halo ketones. Okay, so this is alpha haloketones in the presence of base catalyst. Okay, NaOCH3. So this is base catalyst. So what is the product? So we know that this is Na plus OCH3 minus. Okay, so in first step we know that base will remove H plus ion. So in this case we have two hydrogen here. Okay, so one hydrogen will be removed this side. Here, and this is a negative charge. Okay, so then this negative charge will attack this halogen center and this group will be removed. Then finally we get cyclopropane ring. Okay friends, so this is a cyclopropane ring. Then OCH3 minus. Okay, so this will again attack electrophilic center and this bond shift towards oxygen. Then we get the cyclopropane ring, and this is O negative charge and this is OCH3. Okay friends, so we know that these are the symmetrical structure, so this bond or this bond, so any bond will be break. Okay, so when this negative charge shift towards this side and this bond or this bond will be shifted. Okay, so for example this bond will be shift towards this side. Okay, so then we get this is negative charge because this bond will shift and this is OCH3, this is double bond O. Okay, so after NaOCH3, okay, so protonation will be occur, so we get final product OCH3 C double bond O. Okay, so this can also be written as COOCH3. Okay, so this is the final product for this reaction. Okay friends, so this type of questions will asked. Okay, so let's take one more example. For example, we have 4 ring. This is chlorine atom, this is okay. So we know that in first condition we have a OH minus, second condition HCl. Okay, so you know that OH minus will remove alpha hydrogen or H plus will be removed this side, so this will attack this side, then we get negative charge double bond O. This is chlorine atom, this negative will attack this side, then chlorine will be removed. Okay, so then we get this type of product. Okay, so then after in our solution we have OH minus, again OH minus will attack electrophilic center, then this bond shift towards this side, finally we get this type of structure. Okay, this is OH group. Okay, again this negative charge shift towards this side, then one cyclopropane ring will be removed. Okay, So this cyclopropane ring will, for example, this double bond shift towards this side, then this bond shift towards this side. Okay, so finally we get this is negative charge and this is OH group double bond O. So after protonation we have OH or H2O, okay, water molecule, then we get this type of product. So this can also be ester group COOH, carboxylic acid group. Okay, so COOH. So this is the final product for this reaction. Okay, so these are some examples of Favorskii rearrangement reaction. So thank you friends.